While this course is on macroscopic classical thermodynamics, any modern course in macroscopic thermodynamics touches upon microscopic interpretation, especially of entropy. It gives you pointers on where you can go and learn more. There's a section in the textbook on microscopic interpretation of entropy, but the way I'm presenting the material is the way I think I'm most comfortable, or at least the way I want it to be presented. All right, so where do we stand on entropy? So right now, we have looked at entropy from different perspectives. We've established there is a new state function that emerges from the analysis of Carnot cycle. Carnot cycle is a reversible cycle, and we argued that entropy is a state function. We also gave some computational procedure on how we can get a magnitude of entropy. So we defined it for a reversible heat transfer at a particular temperature. And we also proved a very important statement on how to conceptualize irreversible processes. We talked about generation of entropy, and we emphasized that entropy is not a conserved quantity. Okay, so most of the quantities which you see in engineering analysis, momentum, mass, energy, they're all conserved quantities, but entropy is not a conserved quantity. And we also stated that the entropy of an isolated system at equilibrium can be zero. The changes in entropy can be zero, but it tends to increase left to itself. So what is the agenda? The agenda of the section in the textbook is to answer this question: what is entropy? So this is a broad agenda, actually. We can spend many lectures, which we don't have. So I'm going to keep it limited in scope. And the way I'm presenting it is to make entropy more intuitive to you. Okay, so that's the way get a better physical picture. That's the picture I wanted as an undergraduate student when I was your age. So that's the way I'm presenting this material. Okay, so the scope of the answer is pretty much similar to the way we started discussing internal energy. Okay, we wanted to go beyond mechanics to thermodynamics. So we interpreted thermal energy in terms of kinetic energy of atoms and molecules, how you can store kinetic energy in molecular degrees of freedom. It can be translation degrees of freedom, vibrational degrees of freedom, rotational degrees of freedom, and so on. So we stated, we didn't prove from equipartition theorem, every excitable degree of freedom has half kT in it. We interpreted temperature as a measure of average kinetic energy stored in each degree of freedom. So to get a physical picture of internal energy, we appeal to internal structure of matter, right? Even though we are looking at internal energy from the sense of continuum classical thermodynamics, we appeal to the existence of atoms and internal degrees of freedom and interpreted internal energy. Likewise, we want to appeal to internal mechanics of matter, and can we get a better physical picture of entropy? That's the agenda in front of us. So useful pedagogical example that is often used in most of the elementary textbooks of thermodynamics, statistical thermodynamics, is this gas chamber. This material, this picture I took from this book. It's an undergraduate book on what I would call the modern day version of Feynman lectures in physics by Professor R. Shankar from Yale University. His lectures are also there on YouTube. It's very worthwhile going over the entire set of lectures. At least you can go through the 4 lectures on thermodynamics that is within the scope of this course. So what is the system we have? So to begin with, we have ideal gas. All the gas atoms are distributed in this side of a chamber, and there's a partition. And when you remove the partition, what happens at equilibrium? All the gas atoms are more or less uniformly distributed into the entire chamber, right? So you call this state 1, you call this state 2. So the question in front of us is, why does this process appear natural? Like supposing if we take a video movie out of this entire process, this you will see free expansion at equilibrium. Finally, everything will be uniformly spread. After that, you cannot really make a difference. Okay, so every snapshot will appear to be the same. That's where you say you've attained equilibrium. So note that this is an isolated system. There is no heat interaction or work interaction between this entire chamber and the environment. So even when you make a movie and when you reverse the reverse movie appears to be unnatural, right? So what is unnatural about it? Is it something to do just to do with our perception, or something to do with more fundamental laws not being obeyed? If so, what is the law that is being not obeyed? So is it the first law of thermodynamics or some laws of classical mechanics or something like that? So that's the question. That's the kind of question we want to address. So you would say that this spreading uniformly is a spontaneous process, but all the gas molecules going to one side of the chamber, okay, it is not spontaneous, it's not natural, it's unnatural, right? So that's the statement you would make without any further analysis. Why so? Okay, why is that you seem to feel one direction, okay, this direction, okay, when you remove the partition, that is natural, but the opposite direction, okay, seems unnatural. That is all the gas molecules somewhat crowding around into this, okay? So see, note, these are all ideal gas molecules. So these are point particles. They don't occupy any volume. There is no interaction between them. It's not that these gas molecules have some repulsive excluded volume interaction, okay? So there is no interaction, okay? So energetically, this cannot be differentiated from this. So how do you go about analyzing? So let's calculate entropy, okay? So as Q is 0, because this is an isolated system, there's no heat interaction, and it's a free expansion also, right? So can we say del change in entropy going from this state to this state is Q by T is 0? This seems odd, right? Why is it odd? It's wrong because our computational procedure for getting changes in entropy is applicable only for a reversible process. We have to identify a reversible process which will help us compute entropy. So to compute entropy from what you've learned from classical thermodynamics, we have to identify an equivalent reversible path. So let's go about doing this. So let's note that this is an isolated system and it's a free expansion. Therefore, Q is 0. There is no heat transfer between this entire chamber and the environment. And there is free expansion. The work is also 0. So work interaction is also 0. Therefore, the internal energy of this state is the same as the internal energy of this state. Therefore, the temperature of this state is also temperature of this state. Okay? So let's address this question. How do you identify an equivalent reversible path? So what happened in state 1, we were at high pressure, let's say half the volume as state 2. Okay, this is not drawn to scale, but assume that the volume of state 2 is twice that of state 1. Okay, so we went from this point, state point, to this state point. So there are many reversible paths. So to compute entropy, we have to identify a easily computable path. Okay, that's what we want to do. Okay, so this is one such path, but we will see which path is facilitates computation of entropy. Okay, so we are going to choose a path like this. Okay, so first we decrease the pressure, keeping the volume the same, and then we take this path. Okay. All right. So let us see why we chose that path. So we already mentioned these constraints from simple analysis, and we also said that V2 is twice that of V1. So because del U is 0, you can say Q is P dV. So there's no work done here. So to calculate entropy change, S2 minus S1, we used a formula Q by T under reversible condition, and we substitute PdV for Q, and we get this. Okay, this just follows from ideal gas law, right? So we substitute the ideal gas law into this expression for P. So we get P here nRT by V. This T gets cancelled. Therefore, we get this. N is the number of moles within the system. So from this, because V2 is twice V1, we can get further simplification. All I've done is substituted R, the gas constant, in terms of Avogadro number times Boltzmann constant. This you must have seen from high school. There's a reason why I've presented this in this manner. So what is that you get? I get the change in entropy to be as N, which is the number of gas atoms present in the entire chamber, times the Boltzmann constant, times ln 2. Okay, so this 2 comes from this thing, right? So this is a result from macroscopic thermodynamics. This you should know how to derive this result from what you've learned till this point in the class. So what is the agenda here? So the promise of microscopic thermodynamics is that all the results that you obtain from macroscopic thermodynamics can be derived from certain laws of microscopic structure of matter. Okay, so we take into account the existence of atoms and its behavior, and we postulate that all these macroscopic laws can be derived. Okay, so and people now it's standardized. So chemists and physicists start, in fact, from statistical mechanics and come to thermodynamics. Engineers typically start from macroscopic thermodynamics at the undergraduate level and progress to microscopic thermodynamics, either in a second course in engineering thermodynamics or at least in a graduate course in engineering thermodynamics. So let's see, we're just going to touch upon, okay, just give a sense of how this is done. So the central equation in microscopic thermodynamics is called the Boltzmann equation. Okay, so he's one of the pioneers of this field. So look at the timeline. Okay, so in those times, Boltzmann's theories were not even accepted by his peers. Actually, he killed himself because in those times, you cannot observe atoms. Okay, so now there are ways to observe atoms using, let's say, scanning tunneling microscope, atomic force microscope. There are many ways to visually detect, look at atoms. In those times, there were a set of philosophers, scientists with philosophical, certain kind of philosophy where they claim that you cannot theorize on things that could not be detected, measured, and so on. So Boltzmann theories in those times were not at all accepted. Okay, so the So this is its epitaph on where Boltzmann was buried, and this is the central equation which he derived, which he postulated. We'll see whether it makes sense, this equation. So that's called the Boltzmann equation. So this is entropy. So entropy is defined for a controlled amount of internal energy, volume, and number of atoms. Okay, these are the three things which you control. So this can be controlled for an isolated system. Okay, so for this system, entropy is given by Boltzmann constant times ln of this particular quantity. We will define this quantity in a bit. So this right now is, you can refer to it as degeneracy, is the number of different microscopic states compatible with the macroscopic property. Okay, so let me clarify that. Okay, so for a given macroscopic state, that is, I'm fixing U, V, and N. These are the macroscopic states that fix, these are the macroscopic variables that fix my macroscopic state. For that, I can define many microscopic states. Okay, so how do you define microscopic state? Right at the beginning of the class, we defined, we talked about this. Microscopic state for a particular atom is well defined if you can specify the position and momentum. Okay, momentum along 3 direction and 3 positional coordinates. Once you define that, your microscopic state is well defined for a particular atom. And if you have n atom, there are 6n such microscopic states. Okay, there are large number of microscopic states which are compatible with this 3 variables corresponding to a macroscopic state, because these atoms can take very many positions. Okay, all these very many positions have the same internal energy, so you call it degenerate states. So this is a large number. Okay, so that's one of the reasons why you use ln. We'll see why. What are the other reasons why this equation makes sense? So microscopic thermodynamics is also referred to as statistical thermodynamics or statistical mechanics. Okay, so there were 3 forms of classical mechanics: Newtonian mechanics, Lagrangian mechanics, and Hamiltonian mechanics. So there were certain elements of probability distribution functions that were introduced by Boltzmann and others, Gibbs, and so on. So all these things gave rise to statistical mechanics, and it's also referred to as statistical thermodynamics. So all the properties of macroscopic thermodynamics, okay, the first law, second law, and the third law, can be derived from the microscopic thermodynamics or rationalized from microscopic thermodynamics. Okay, so this has nothing to do with quantum mechanics. Okay, so all these things which we are going to discuss are part of classical physics. So I will tell you a simple computational procedure that is often used, okay, in microscopic thermodynamics. A powerful model is called a lattice model. Okay, so in a solid state where the atoms have discrete translation symmetry, the existence of lattice is rather obvious. Okay, so however, these lattice models are also useful for systems which do not have discrete translation symmetry but have continuous translation symmetry. The fluids, the liquids and gases have continuous translation symmetry as opposed to solids which have discrete translation symmetry. Even for fluids, lattice model is very valuable. Okay, so let's see how you go about computing from a simple lattice model. So you assume a lattice point of volume r cubed. Okay, r is an atomic radius. Okay, so this is a loosely defined property, because to define it precisely it's not possible, but you have some sense on what can be an atomic radius. Okay, this if you your high school chemistry will tell you something called covalent radius, ionic radius, and so on. There are ways of giving a measure to an atom. So you take r to be atomic radius, and r cube is the approximate volume of an atom. Okay, so you assign a lattice point. Okay, these are, see here, if these are, let's say, gas atoms, in this case ideal gas atoms, and these are lattice. Okay, so the entire three-dimensional chamber is divided into equal lattice of volume of R cube. Okay, so you have small cubes of volume R cube, and you are dividing the entire gas chamber into these small lattice points. So number of lattice points is V1 in state 1 divided by R cube. Okay, so most of, when you have a gas, most of the gas chamber is empty. Okay, because these atoms have a very small volume. Okay, so just for the modeling purpose, I'm not assuming it's an ideal gas. Ideal gas R is a point particle, R is 0. For this, we have some sense of atomic radius. Let's say when you go from helium, neon, argon, and so on, there is some sense of atomic volume. So we take one such R and then build this model. Okay, so because most of the gas chamber is empty, our L1 is much larger than the number of atoms present. Okay, so when volume increases, L2 becomes twice as L1. Okay, and again L1 and L2 are much larger than N. So I said omega is the number of ways you can distribute the gas molecules. Okay, so I take the first atom. How many ways I have of distributing the gas atom? I have L1 ways, right? There are L1 slots available to you. Then I take the second atom. Because L1 is much larger than N, saying that whether L, it is the number of ways I can distribute is L1 minus 1, because L1 is so large compared to 1 or N, I can say the second atom also can be approximately distributed in L1 ways. So is the case for third atom, fourth atom, and to the nth atom. Okay, so the number of ways of distributing N atoms into L1 lattice sites is this quantity. Likewise, I can say number of ways of distributing N atoms into in the state 2 is this number. I can just rewrite it as 2 to the power of N times this quantity. So what I'm going to now use the Boltzmann equation and compute the change in entropy. My changes in entropy is S2 minus S1 is K. I'm just putting these into the Boltzmann equation. What do I get? I get this formula, which is the same result that I got from macroscopic thermodynamics. Okay, so what did I gain by doing this? Okay, so I gain a physical interpretation for entropy. See, when we analyze Carnot engine, because this is what I saw in undergraduate, somehow we're not able to get a feel for entropy. It's sort of mystical. It adds to its beauty, but it is not very practical to have that vagueness. Okay, so you want to finally compute something, use whatever you've learned to do, analyze your experiments, analyze technical matters. So what we have here is when you say entropy is a state quantity, okay, it's a state function. Okay, we want to be able to associate some property of the state you are looking at, right? So when you are looking at a particular system, there are a number of ways you can distribute the atoms in that particular state. Okay, so that's the interpretation we are going to utilize for entropy. We will look at this the next couple of slides also. What is the caveat of the model? Okay, so this model is limited in a particular manner. Okay, so we have not talked about momentum at all. Okay, so if you remember, for specifying the microscopic state, we need to specify the position as well as momentum. Okay, so you can see we said the position, we accounted for the positional distribution by saying that we are going to distribute these atoms in these n lattice points. But momentum states we didn't really care. Okay, so why that is so? Because this is not a very general example. This is just a pedagogically useful example, because in a free expansion, the internal energy does not vary, okay, from state 1 to state 2. So the momentum distribution also does not vary. So because of which we neglected the momentum distribution and came up with a simplistic analysis. But those things can also be accommodated. Okay, this is just this model has a pedagogical utility, because we have limited time in this course to address microscopic thermodynamics. So it is limited, but still very insightful. Okay, so if there are questions, we can discuss this in the discussion hour next week. So, okay. So the next thing, let's try to understand whether we can make more sense of certain things you've heard about entropy. We always say there are certain spontaneous processes which increase entropy, right? So let's ask the question, why does entropy increase when you go from state 1 to state 2, okay? The number of ways of distributing atoms after you remove the partition, okay, when you go to state 2 is much more, right? Each here, I had, if I take, let's say I divide it into 2 states, okay? Each atom can either go into this state or this state when I'm in state 2, okay? But whereas when I'm in state 1, all the atoms had to go into this state alone, okay? So the number of possibilities for each atom increases by 2. So for n atoms, it goes as 2 to the n, okay? So the number of ways of distributing microscopic matter increases when my entropy increases, okay? So entropy is associated with the way you can distribute atoms corresponding to a particular macroscopic state, okay? The microscopic distribution, spatial as well as momentum distribution corresponding to a particular macroscopic state, okay? So that's the way we are going to interpret entropy. So when you go from here to here, there are many ways of, look, n is a very large number, right? Avogadro, the order of Avogadro number. 2 to the n is a humongous number, okay? So there are many more ways of distributing the atoms uniformly, as opposed all the atoms crowding into some corner, okay? So it is, it doesn't violate first law of thermodynamics, but it is probabilistically impossible that all these atoms somehow crowd into one particular part of the gas chamber, okay? The reason why it is the gases are uniformly distributed is that the number of ways of gas being uniformly distributed is much more than number of ways of it being non-uniformly distributed, okay? So it is just a matter of combinatorics. It's a matter of numbers. Okay? This is the way large numbers, when you have large number of atoms, behave. Okay? So as I said, thermodynamics is a macroscopic science, right? You have to have large number of atoms to even define macroscopic properties. When you have large number of atoms, we can analyze them in a particular manner and then come up with these conclusions. So what is spontaneous is what occurs naturally. Okay, there are many more ways of occurring naturally. Okay, so this state seems natural compared to all these gas atoms being crowded in some corner. That is because the number of ways of distributing them uniformly is much more than number of ways of distributing them in a non-uniform manner. Okay, again, that's a important statement, so I've emphasized it a couple of times by repeating it, but if there are questions, we can discuss it during the discussion. So here we talked about one spontaneous process, but other spontaneous process like mixing can also be addressed, okay? Heat dissipation, okay? All the things which involve increase in entropy can also be rationalized from microscopic. What do you mean by mixing? Supposing I have red spheres, okay? In one part, and then I have let's say black spheres, and I have white spheres, okay? And then I remove the partition and then jiggle it around, okay? When I jiggle it around, when I shake it around, after a considerable shaking, let's say all these white balls are mixing with, they're changing their position with the black balls. Ultimately, let's say equilibrium state for that particular system is that the white balls and black balls will be uniformly distributed. Okay, that's corresponding to something like that. Okay, you will never have the case where in some suddenly all the white balls are in one half of the chamber and the black balls are in the other half of the chamber. Okay, so I'm just talking about hard spheres, like you take wooden spheres, one is colored white, another is colored black, and when you shake them for long enough, they will all mix together. Okay, so these things, so many things associated with entropy, because much more intuitive, makes sense if you ask the question, how many ways a state can be arrived at. Okay, so here, this state, there are many more ways of arriving at this state. Okay, so again, we came up with this equation, Boltzmann came up with this equation. Is this intuitive? Have we substituted one equation for the other? Okay, so we said that when we looked at entropy formula, we discussed this a lot during the last discussion hour also. It doesn't look so intuitive. Does this, this interpretation of entropy has some utility, but is this equation intuitive? So one way of asking that question is, entropy is an extensive function. So if you have subsystems, you can write total entropy as S1 plus S2. 1 and 2 are subsystems. So the number of ways of distributing the first subsystem is, let's say, omega 1. The number of ways of distributing the second subsystem is omega 2. So the total number of ways are omega 1 times omega 2, right? These are two independent subsystems. So when I take logarithm, I still have the total entropy behaves like what we know of classical entropy, okay? Classical macroscopic entropy. That's one of the justification, and there are other justifications too, okay? So why Boltzmann used long term, okay? Log or long term. So there are ways of thinking about it, okay? So that completes the Boltzmann version of microscopic thermodynamics. So what system did Boltzmann look into? Boltzmann looked at a macroscopic experiments that is conducted with controlled internal energy, total volume, and total number of atoms. Okay, this is an isolated system. And he arrived at the Boltzmann equation. And there is another equally large figure in history of thermodynamics, Gibbs. Okay, so he looked at an experiment conducted in a different manner. Okay, so the macroscopic system you're looking at is not an isolated system, but it is a system whose temperature is fixed. Okay, how can you fix the temperature? You can fix the temperature of system by having that system in contact with the thermal reservoir. Okay, so this system can exchange energy, but its temperature is the same as the thermal reservoir. So he looked at a different macroscopic constraint. The macroscopic constraint, it controlled the temperature of the system, volume of the system, and the number of atoms. Okay, so that was fixed. So that's not an isolated system. Okay, so corresponding to that, he derived an equation that looks very similar. Okay, but it's yet different. Okay, so these are the three macroscopic constraints in an isolated system. For the Gibbs formalism, the macroscopic constraints are these three macroscopic thermodynamic variables. And this is what is a partition function. This is also called partition function. This is the Boltzmann constant, this is the Boltzmann constant. So this is a natural thermodynamic variable. Okay, which in a way you will, if you go and take a course in statistical mechanics, statistical thermodynamics, you would say this natural thermodynamic function is extremized. It takes up an extrema, okay, either a maxima or a minima. In this case, it's a maxima. In this case, it will be a minima. Okay, so corresponding to a set of macroscopic constraint, there is a function which is going to take an extremal value. We'll see this towards the end of the course again. Okay, this is not anything specific towards microscopic thermodynamics. This is something that can be shown from macroscopic thermodynamics. Okay, so what is this Z? Okay, so we said that you have a macroscopic system that is in contact with, let's say, thermal reservoir. So for this macroscopic system, the energy can fluctuate. Okay, so we assign the probability of finding this macroscopic system with a particular energy and assign some probabilities. Okay, see, this might not be clear to you. I can understand because this takes a couple of lectures to clarify this. We introduce a notion of an ensemble and we set up the problem and analyze this. But in the absence of such lectures, I'm just trying to give you a flavor of microscopic thermodynamics so that you probably it will inspire some of you to go and take up a course in statistical thermodynamics. Every department, chemical engineering, materials engineering, chemistry, physics, offers such a course. So if you find these things interesting, hopefully you can take this as an open elective or department elective. So we can assign a probability for finding this macroscopic system at a particular energy. And then this is called a partition function. This can be interpreted as an average degeneracy of a system. Okay, so here also we interpreted this partition function as the degeneracy of the system. Okay, degeneracy means number of microscopic ways of distributing the system corresponding to a particular macroscopic constraint. Okay, I won't hold you responsible for understanding this particular point. Okay, but I'm just trying to give you a flavor for what we do in microscopic thermodynamics. This is a surrogate for the section in your textbook which talks about what is entropy. Okay, it tries to address it, but I was not satisfied. I wanted to present it in the way which I feel more comfortable. So we call this quantity Z as the canonical. Canonical, this is another word for typical. Canonical partition function. Why is this typical? Because most of your experiments, it's much more easier to control temperature. Okay, so it is usually you equilibrate the system with respect to atmospheric temperature. So that's the typical system, typical macroscopic system which you're trying to analyze. That's called a canonical partition function. This partition function, which Boltzmann analyzed, is called a microcanonical partition function. Okay, so that is why you call this microcanonical, because a canonical partition, canonical ensemble. Okay, ensemble means it's a set, right? You know, a group. Okay, you know what's a musical ensemble, right? It's a group of entities. Okay, so you would see that your canonical ensemble is a superset of microcanonical ensemble. Okay, I'm not going to hold you responsible for all these things, but if somebody is interested, we can discuss this further in your discussion hour. But this is just to give you a flavor of what we do in statistical thermodynamics and so on. Okay, there is a more complete version of entropy. Okay, so it comes from information theory. Okay, actually, so this is called Shannon's measure of information. So where you associate a quantity H with probability distribution function. Okay, so entropy, you would say that it's a very general concept. You will see in financial markets, you will see in many cases. Okay, so how do they associate entropy? Okay, so all these things has a basis in Shannon's theory. Okay, so Shannon was able to associate a quantity H with any general probability distribution function. Okay, so if you have set of events and associate continuous probability distribution function, you can come up with the quantity H, and you can correlate that H with entropy and Pi with certain thermodynamic properties. Okay, so probability in phase space. Okay, so that can be done. Again, I'm not going to hold you responsible for this. Just to give you pointers. Okay, so I feel one of the objective of these courses is to give you a foundation of what is understood and where you can go and learn more. Okay, so if you find some part of the course more interesting, you know your interest and hopefully go and take some courses. We have a lot of flexibility in the way you can take department electives and open electives. So use this flexibility to go and learn further. Okay, so I suppose there are some courses in the institute which also deal with Shannon's presentation of entropy. Okay, so this is a very general formulation, very powerful formulation, which at least you should know that there is one such formulation, so that you can, if interested, you can go and learn. Okay, so it can be correlated. H is more general than entropy. It has to do with information, and but it can be correlated to entropy, and this K, which is a more general constant in Shannon's measure of information, it can be correlated to Boltzmann constant in particular setting, in particular systems. Let's wrap up here. So this a table which is from Feynman's lectures in physics. It's a very nice table which succinctly presents all the laws of classical physics. Okay, you have the classical mechanics and the masterpiece of Maxwell, electricity and magnetism. All these things are mechanical variables. Okay, so in all these equations, you don't see temperature at all. Okay, so what completes the classical equations are these two equations. Okay, so Boltzmann's equation, Boltzmann equation, and Gibbs equation, these talk about a system of thermodynamic equilibrium. These introduce the notion of probability distribution, notion of temperature. This wraps up all the equations that are associated with classical physics. Okay, classical physics was complete by about 1900. Even see what you call as the modern classical physics is probably associated with kinetic theory, plasma physics, and so on. There are some new equations that came about, but more than 90% of classical physics, okay, in exclusion of, let's say, plasma physics and so on, okay, so certain issues of phase transitions, all these things were complete by 1900. Okay, so from there, what we call as modern physics are associated with quantum mechanics. Okay, so see, in classical physics, we look at physics of particles, physics of fields, right? Likewise, in quantum mechanics too, you have quantum mechanics of particles and quantum mechanics of fields. Okay, so all the physics which comes after 1900, we lump it as modern physics and teach it in a particular manner. So all the equations of classical physics are present here. With this, you at least know the equation. How do you use this equation to analyze many systems? That's the challenge you should undertake. Thank you. With this, I will complete this lecture.